Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 26, 2025, just yesterday. It introduces a new benchmark for embodied cognition and shows that even top vision language models nearly collapse to zero accuracy on long interactive sequences, while humans stay around 93 to 97%. The paper is titled ENACT, Evaluating Embodied Cognition with World Modeling of Egocentric Interaction. And, as we will see later, the way this benchmark separates true world modeling from surface-level pattern matching has big implications for how we train future models. Also, the authors shared a GitHub repo for ENACT. There you'll find the full benchmark code, a pip installable package and conda setup, scripts to download the QA and simulation datasets, tools to run evaluations with ENACT eval, and a complete pipeline to generate your own egocentric data and QA tasks. Alright. Figure 1 lays out the whole idea of ENACT as world modeling from an egocentric agent. The left panel depicts a partially observable Markov decision process, where scene graphs evolve as actions like putting a plate inside a fridge or opening the door change the world. The middle panels define the two tasks. Forward world modeling orders future images given actions, while inverse world modeling orders actions given images. The bar and line chart below show that humans stay accurate across long sequences, whereas a model like GPT-5 drops sharply, especially for forward prediction. The right panel illustrates that these questions span many everyday activities, from cooking to laundry to loading a car trunk. Well, Figure 2 explains how those egocentric questions actually get built. The top strip shows dense mobile manipulation demonstrations, where a robot moves and interacts at 30 Hz. The middle strip highlights only the keyframes where the symbolic scene graph changes, such as grasping a drill or putting it inside a box, which drastically compresses the sequence. The right side then samples many shorter trajectories from these keyframes, and the bottom row turns each trajectory into forward and inverse world modeling question-answer pairs. Alright, Figure 3 grounds that pipeline in concrete examples. The left panel shows diverse household scenes and a word cloud of objects and predicate labels, which highlights that questions span many rooms, tools, and actions, like opening, grasping, or placing items. The middle panel illustrates a forward world modeling question, where shuffled future images must be reordered given textual action descriptions. The right panel mirrors this with inverse world modeling, where the images are fixed and the shuffled action snippets must be put back into a causally consistent order. So, after those qualitative examples, Table 1 reports pairwise accuracy for many vision language models across different sequence lengths. The table shows that inverse world modeling almost always scores higher than forward, especially once the horizon exceeds 6 steps. Proprietary models like GPT-5 and Gemini 2.5 Pro lead the pack, but still deteriorate sharply with length. Open-weight models fall even faster, while the human row at the bottom stays around 94 to 97% across all lengths. So, while Table 1 focused on simulation, Table 2 reports how Intern VL 3.5 performs on real robot videos. The table shows that forward world modeling accuracy drops from about 73% at length 3 to essentially 0 by length 9 or 10. Inverse world modeling stays higher, starting near 90% at length 3, but still falls to roughly 3% by length 10. These parallel declines suggest that the same long horizon weaknesses persist in the real world, so the simulator measurements transfer faithfully. So while Table 2 addressed sim to real transfer, Figure 5 probes how image realism and camera or robot biases shape performance. The top left heat maps show that changing rendering realism barely matters, but widening the camera field of view or using a fisheye lens significantly hurts both forward and inverse accuracy. The lower panels indicate that high camera mounting harms forward reasoning, whereas robot appearance has negligible impact. The right-hand analysis table reveals a clear right-hand bias, with higher precision for right-hand actions and more mixing of true left-hand events into right predictions. Well, Figure 6 drills into what those failures actually look like for GPT-5. The stacked bars compare error types for forward and inverse world modeling, so they show which mistakes dominate. Hallucination in red and omission in orange together occupy most of each bar, meaning the model often invents state changes or misses real ones entirely. Smaller blue, green, and purple segments reflect rarer entity, polarity, and predicate substitutions, which are much less of the story. So the big message is that egocentric world modeling, framed as these forward and inverse reordering tasks, exposes a sharp gap between human embodied understanding and what even top vision language models can do, especially over long horizons. This benchmark therefore pushes future models toward genuine action-conditioned reasoning, not just static pattern matching. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.